Okay, in this problem, I'm going to solve 446 in Hibbeler. So this is a statically indeterminate problem, except it's a little different flavor. So I guess, it's hard to kind of find different varieties of this, but here's one. So here's a stepped axial structure. So you have two sections, different diameters. They're solid, made out of steel. There's walls at both ends, but initially there's a gap here of 15 millimeters. So the gap is there before the load is applied. Then we apply a force on here of 200 kilonewtons, and it wants you to find the support reactions at A and D. Okay, so what's going to happen here is if the force at P is sufficient to elongate this such that it comes into contact at D, then it'll become a statically indeterminate problem. All right? So probably you can infer from this that they set up the problem such that P is large enough that this section stretches more than 15 millimeters. Then obviously we have a statically indeterminate problem. We need to figure out the reaction forces X, D, and A. If P isn't big enough to stretch that 15 millimeters, then the fact that this wall is here, it's never in contact, is irrelevant. It becomes a statically determinate problem. And then the reaction force at A is going to be the negative of P, and the reaction force at D will be 0, right? Okay. All right, so technically we should first check the elongation, all right? All right, so let's check the total elongation. So let's check the elongation as if the wall were not there. All right, so forget the wall and just figure out the elongation. So let's get the cross-sectional areas of the sections first. The area of the section from A to B is going to be pi on 4 50 millimeters squared. Let me get my calculator for just a second. So that is 0.00196 meters squared. And the cross-sectional area from B to C is pi on 4, 25 millimeters squared. So that is 0.000491 meters squared. So those are the two cross-sectional areas. All right. So now the total elongation is the elongation of section AB plus the elongation of section BC. All right. If we do the free body diagrams, here's point C. Assuming it's not in contact, then there's no force on here, so obviously the internal reaction force here is 0. The only reaction force we have is between section A and B. All right? So here we have the P equal to 200 kilonewtons. So the internal reaction force here is obviously equal to that sum of forces, right? So this elongation is going to go to 0 because there's no force in it. So the total elongation in that case is just the elongation of section AB, which is the force in that section, P AB, times the length of section AB over the cross-sectional area times Young's modulus, and they're all constant, all right? So that gives me delta is equal to 200 kilonewtons times the length, which is 600 millimeters. The millimeters will cancel out with the kilonewtons. The area is 0.00196 meters squared. In Young's modulus, it's made out of steel, so that's going to be 200 gigapascals, okay? Then when we compute that, that turns out to be 0.306 millimeters, okay? Which is obviously greater than the 0.15 millimeters. So that means it's going to be in contact. All right. Well, so now we know we have the statically indeterminate problem, which we probably suspected earlier. So there's two ways you could do this, right? We could go back and let's do two approaches. So here's the first approach. The first approach is sort of the conventional way. We have two equations and two unknowns. So we have sum of forces in the x have to equal to 0. Or in other words, the reaction at A plus P plus the reaction at D all sum to 0. Okay? So this is assuming here. Here's a reaction force at A, and here's a reaction force at D. Now I know probably that's also going to be in compression, right? And this one's the signs are probably flipped, but I'll just put them in the positive direction for now. So you have two unknowns. You need another equation. We use the compatibility equation. The total elongation, which is the elongation of section AB plus the elongation of section BC, has to equal, not 0 in this case, but has to equal the 0.15 millimeters. So we know the elongation is going to be this gap distance, right? That's how much it elongates. And then it comes in contact, and then the reaction force is such that that is the elongation, all right? If the gap were longer, then you would have a bigger distance here. So what that's going to do is automatically compensate for the fact the amount it stretches before it comes into contact. So that's one approach, and you could certainly solve those two equations, the two unknowns. We can set it up real quick. This is going to be the force in section A. Now be careful, we have to use different free body diagrams here, right? Now if we look at section A, or section AB, here's the reaction at A, and then here's that internal force in section AB. So that's going to equal minus the reaction at A. And likewise, in section BC, here's the free body diagram for the section BC. Here's the reaction force at D. Here's the internal reaction force in that section. Again, it's on a negative face, so I draw it so it's positive in tension. This has to be equal to RD, okay? They have to equal to 0. All right. So in this one, this would be the force in AB, which is minus RA, times the length of AB, over cross-sectional area of AB times the Young's modulus. And then this is plus this section here. So it gives me a plus the force in BC, which is RD, the L of section BC, cross-sectional area of BC, Young modulus, and that all sums to 0.15 millimeters. So you can do that. Actually, I'll do the superposition approach. Why? Because I've already done half of the superposition problem, right? The superposition problem is, right, you remove the constraint, make it a statically determinate problem, and then apply the appropriate force so that the elongation makes it compatible, okay? So if you look, I've already gotten the first subcase for the superposition approach. So let's do it that way. Let's do super. So we'll use the superposition approach. So basically, we're going to take this problem with the force P applied here, and we're going to superimpose on it this problem. Well, let's keep the reaction force, let's keep it in the same direction. And that's the unknown reaction force RD. Okay? All right. So this case here, we've already done. Okay? That was actually the first part that checked that it extended too far. So now let's solve this case. So in this case, again, it's quite easy. I'm going to call this case 1, and this is load case 2. So now let's look at load case 2. So what I'm saying, I already did this before, just to I should notate it. Uh-oh. This section here, where we found that it's 15 millimeters, actually was the solution to load case 1. So you see I've already done that. Okay, for load case 2, the elongation for loading type 2, that's going to be, again, the elongation of this section AB plus the elongation of BC. And obviously this is using the loading as shown here. All right, so this is easy. We can do the free body diagram. Obviously, in this case, the reaction force at the wall is minus RD, and then both of these sections have the same internal reaction force of just RD in tension, okay? And so in this case, right, the elongation is going to be RD times the length of AB over the cross-sectional area of AB times Young's modulus plus RD length of BC, cross-sectional area of BC, Young's modulus, right? So this term here is the elongation in the first section, and this is the elongation in the second section for this loading. All right, so I can take the RD out. Delta 2 becomes RD. Let's put in some numbers here now. So the length of AB, they're both 600, so actually I can take that out as well. Well, let's put it here. Well, actually, I'll do it this way. 1 on the cross-sectional area of AB, which is we got to be 0.0196 meters squared. The cross-sectional area of BC is 0.00. I'm missing another 0 here. 0.00196, and this is 0.000 0.491 meters squared. The L actually happen to be the same in this problem. They're both 600, not normally. And the Young's modulus is the same. So we can just take the 0.6 meters over Young's modulus, which is the 200 GPa. All right? And then this becomes, let's do the math. .639 times 10 to the minus 9th. Now the units we're going to have here, I put this is all in MKS, so this is going to be we have meters, we have a meter squared times meter, so I got a meter down here. This is a Newton per meter squared, so this just becomes meters over Newton times RD equals the displacement, okay? So if this is in newtons, this becomes meters, right? Okay. So now what's the situation? So we know that the elongation for the first loading case, we already computed that out. That is the 0.306 millimeters. And the displacement for the second case is going to be this 7.639 times 10 to the minus 9th meter newtons times this unknown reaction force. The actual displacement has to equal the sum of those two. All right? That's the superposition. We take the loading here, or the displacement, stick this way. This has a displacement, and then this also has a displacement. The actual displacement, when you apply both forces, is the sum of those two displacements because of superposition. And that still has to go to 0.15 millimeters, okay? So again, we know the total displacement has to be 0.15 millimeters. So this, I can rewrite this. This is 0.306 millimeters plus this term, which is here. Let's convert this to millimeters. So this becomes 7.639 times 10 to the minus 6 millimeters over newtons, that's not an M, Newton, times RD has to equal 0.015 millimeters. And now we can solve for RD, right? RD is going to be 0.015 millimeters minus 0.306 millimeters divided by 7.639 times 10 to the minus 6 millimeters over Newton. So this result will be in newtons, and that becomes 0.15, okay? 0.15, 0.306 minus is a negative 0.156, and then 7.639 to the minus 6. We divide, and that becomes minus 20.4 kilonewtons, okay?
So that's the reaction at D.
It's the unknown reaction at D. All right.
So if you get the reaction at A, well, we know that the reaction at A plus the reaction at D plus the applied force at P have to sum to 0. And so that gives me that the reaction at A is simply going to be minus the reaction at D minus P, which is 20.4 kilonewtons, a minus and a minus, and then P is 200 kilonewtons, so it's a minus 200 kilonewtons, so that gives me sorry, I did that wrong. 20.4 minus 200 gives me a minus 179.6 kilonewtons. So it's acting in the opposite direction. So actually, if we were to look back at this picture and redraw in the values of the correct signs, like I'll do it in red, what we actually have here is at RD, we have a negative reaction force here of the 20.4 kilonewtons, and then at RA, it's a minus sign, so it actually acts in this direction, 179.6 kilonewtons. Okay? So those are the reaction forces. So again, two approaches, right? You could do this direct approach, where you have the two equations directly, the sum of forces and the compatibility equation, okay? Or you could do the superposition. Again, as I mentioned in class, I like the direct approach, but superposition worked in this case because, in fact, if you didn't infer, obviously, that it would come in contact, you would want to check that it did elongate at least the gap of 0.15 millimeters. So by doing that check, I'm sorry, I'm pointing to the wrong spot. Here's the direct approach. By doing this check, that's actually the first step, or the first load case we're considering for the superposition approach, right? That actually becomes the same as the check, okay? So, kind of kill two birds with one stone. All right, thanks.